This is also my first visit to this meeting, so it's really exciting to be here. So thank you very much for that opportunity. So my name is Mary Knapp. I am a research scientist at MIT Haystack Radio Observatory. We're the off-campus radio observatory in a place that used to be radio quiet and isn't really anymore. So what I am here to talk to you about today is radio astronomy from space, specifically low-frequency radio astronomy, which is really kind of the last unexplored part of the electromagnetic spectrum, and therefore a really exciting opportunity. So this view of our galaxy, the Milky Way galaxy, is what we can see with our eyes. This is optical. So this is what humans have been able to look up at the sky and see if they're in a particularly dark place for as long as we've been looking up at the sky. In the last decades, we've built different kinds of detectors and telescopes and vehicles for those telescopes to open up other parts of the spectrum. So this is infrared, a couple of different bands, and you can see the view of the galaxy changes. We can see into the center of the galaxy, whereas in the optical, dust gets in the way. And we keep going down the electromagnetic spectrum into radio, which we can observe from the ground, all the way up to about a few hundred megahertz. We go the other direction as well, to the high energy part of the spectrum. So this is X-ray and gamma ray. And with our technology, our detectors and our spacecraft in some cases, we now have this beautiful multispectral view of our own galaxy that you can see here. And every time we've opened up a new part of this spectrum, we've found something unexpected. So for example, when we first started doing radio astronomy from the ground, we discovered pulsars, which were not expected. At the high energy end, gamma ray bursts were somewhat of a surprise and continue to be a really fruitful area of study. And of course, now we have multi-messenger astronomy, about which I think there's going to be a very exciting announcement tomorrow, I think. But there's a piece missing from this picture, and that's at very long wavelengths. And the reason for that is the Earth's atmosphere, in this case, specifically the ionosphere. So this is the transmission of the Earth's atmosphere as a function of wavelength. So in the visible, we can see through some of the infrared, big window in the radio, but at high energy, some of the infrared, where JWST observes, and down here at low frequencies, we can't see out of our own atmosphere. So we have to build spacecraft to get above that atmosphere and do the science that we're interested in. And at low frequencies, it's the ionized part of our atmosphere that causes the problem. So what? What is there to see at long wavelengths? This is 10 megahertz, 30 meters, and down, so into wavelengths that are kilometers in scale. So what is there to see? Well, it turns out there's a lot of things that we know we can look for. We heard a wonderful talk just in the previous session about the potential for cosmology exploration at low frequencies from space. I'm not a cosmologist, so I'm not going to get into that. There's also interesting science to be done more locally, looking at the interstellar magnetic field in the plasma that spans the space between stars. There is tremendous opportunity within our own solar system in heliophysics, looking at space weather. What is the sun doing and how does it affect other planets? And also simply making maps. When you make a map for the first time, almost inevitably you see things that you didn't expect. We have some sense of what we expect the sky to look like at low frequencies. It's not like we have no idea, but inevitably there will be surprises, which is very, very exciting. So I don't really work in any of these fields, but I am an exoplanet scientist, so that's what I'm going to talk to you about today. So back in the 50s, when radio astronomy on the ground was really getting going, Burke and Franklin detected radio emission from Jupiter at about 20 megahertz, and it was periodic and quite strong. And from that, they were able to deduce both the rotation period of Jupiter and the magnetic field strength of Jupiter, because they correctly inferred that the radio emission that they detected was from something called the electron-cyclotron maser instability, which is a process that happens through the interaction of charged particles in magnetic fields in the auroral zones of planets with strong magnetic fields, like Jupiter. And this type of radio emission is coherent and it's produced at a frequency that corresponds directly with the magnetic field in the region where it's produced. So it's a tracer for magnetic field strength. So Burke and Franklin were able to measure the magnetic field of Jupiter long before we sent spacecraft to do that in situ. So planets with dynamomagnetic fields, internal fields that are relatively strong, produce radio emission through this cyclotron mechanism that is beamed, as you see in this nice illustration, in a large hollow cone. So it goes around like a lighthouse, so something like a pulsar. It is at a frequency that's proportional to the magnetic field strength. It tends to be bursty, but also periodic with the rotation period of the planet. And in the case of planets with moons in certain locations, like Jupiter, the orbital period of the moons also has an imprint on the radio emission. And finally, this type of radio emission is circularly polarized, which matters because not a lot else in the sky is strongly circularly polarized like planetary emission is. So it's a really helpful way to separate it out from all of the other signals floating around in the sky. So here's a portrait of our own solar system in planetary radio emission. So this shows frequency versus flux density, and I put Jansky's on here for the radio astronomers in the room. Oops, getting ahead of myself. So here's, whoops, sorry, wrong button. There we go. Here's Jupiter. This messy curve is Jupiter. Jupiter has the strongest planetary magnetic field in the solar system, and therefore its radio emission is at a higher frequency than all the others. So you can see that here. And it's also affected by its volcanic moon Io, as well as the other Galilean satellites. So there's a lot going on. These spectra are the rest of the solar system planets that have strong magnetic fields. So here's Saturn. Saturnian kilometric radiation is SKR. Earth is here, terrestrial, Uranus, and Neptune. And what you'll notice is that the frequencies, the peak frequencies, are much lower than Jupiter, which means we can't see these from the ground. Only Jupiter's radio emission is detectable from the ground. So we had to wait for Voyager 2 to do its grand tour before we were able to make this solar system family portrait. And so this is analogous to exoplanets. We likely, although it's challenging for technical reasons, will be able to detect Jupiter-like magnetic fields of exoplanets if we, whoops, stop going forward without me, if we have sufficient sensitivity in ground-based telescopes, but not planets with magnetic fields like the Earth, or Saturn, or Uranus, or Neptune. So going to space will open up the full spectrum of exoplanets to this type of characterization as well as potentially detection. So I want to share a sonification of Saturn's radio emission. This is time versus frequency, and the color is intensity as measured by Cassini. And it's basically been shifted in frequency so that it's in the range that humans can hear. So if you were able to tune your radio to Saturn and do the frequency shifting, this is what you would hear. So, to be honest, that sonification is what really sold me on this field. The idea that planets were out there, warbling away at wavelengths that we couldn't access from the ground, and all we had to do was build better telescopes so that we could hear them. That was it. I was sold. I want to hear our solar system planets, and I want to hear the songs of exoplanets too. So that's interesting aesthetically, artistically, if you like. What about scientifically? What is the scientific value of making observations like this for exoplanets? There are many, many things that we can learn. So the magnetic field strength, as I said, is directly proportional to the frequency. So if we can measure the spectrum of an exoplanet at low frequency, we'll know its magnetic field strength, which is definitely interesting for the question of habitability. This is complicated, and I'm certainly not going to stand here and say having a magnetic field makes a planet habitable. It's not that simple, but it will have influence on the evolution and retention or loss of atmosphere, for example. So that's one thing. The rotation period, all the canonical rotation periods for solar system gas giants are measured in this way. Also, the other things happening in these systems, solar winds, stellar storms, impacting planets will have an effect that we can measure through low-frequency radio emission. And finally, as with Jupiter, we might even be able to infer the presence of moons if there's additional modulation on top of the rotational modulation from the planet. So what do we need to make these observations? Well, one thing we need is to be above the ionosphere, and that means being in low Earth orbit or above, so a few hundred kilometers above the Earth's surface, and we're above the worst of the ionosphere. Getting a little higher is even better. We also need some angular resolution to be able to tell what we're looking at. So where is the signal coming from? Is it definitely from the location of a planet? And so on. And for that, you need either a very, very large diameter dish, many wavelengths, and we're talking wavelengths 30 meters and longer, or you need an interferometer with relatively long baselines. And finally, you need sensitivity, the ability to detect faint signals. And for that, you need, again, large collecting area, whether that's a very, very big dish or dishes, or an interferometer with many elements. So currently, we have spacecraft that are sensitive to these low frequencies. A lot of the heliophysics fleet have antennas that work in this range. These are all single spacecraft. They are able to get above the ionosphere, but they don't have a lot of angular resolution or sensitivity. So I want to talk about a couple of missions that are upcoming that are starting to move forward in developing angular resolution that we can use in this frequency band. So the first one is one that I'm involved in. I'm the deputy PI for the AeroVista mission, which is a pair of 6U CubeSats, which is about the size of like a jumbo cereal box, if you're not familiar with the CubeSats, that we want to put into a polar orbit to fly over the Earth's auroral zones, every orbit, between 450 and 600 kilometers. We will have on this spacecraft a big deployable antenna, which is called a vector sensor, and I'll talk more about that in a moment. This is 4 meters tip to tip, so it's not a small antenna, but it's still electrically small relative to the long wavelengths that we're talking about. So what we want to do is map the Earth's auroral radio emission. We know that the Earth has strong, like up to terawatt strength radio emission from its auroral zones, but we know that in a non-spatially resolved way. So what AeroVista hopes to do with our 2 spacecraft is make a map for the first time, actually. I want to talk briefly about our antenna, because it's one of my favorite things, so please bear with me. We're using a vector sensor antenna. A vector sensor antenna is really just 6 antennas, 3 electric sensing elements, 3 magnetic sensing elements, put together that share a common phase center. So the advantage of this antenna is that it's got 6 measurements, and it just so happens that there are 6 components to an electromagnetic field propagating in space. 3 for the spatial definition of the electric field, and 3 for the spatial definition of the magnetic field. So if you have 6 measurements, you can extract those 6 values, you can take the cross product, and that gives you the direction from which the wave came. And that's why with a vector sensor, you can do direction finding, you can do course mapping, just with one of these, without even bringing interferometry into the equation. So this technology came out of the defense world, and we've spent quite a bit of time working on how to apply it to astronomy and other science applications. So there's another CubeSat mission called Curie. Curie is a set of 2 3U CubeSats, so these are half the size of the AeroVista CubeSats with a different kind of antenna. And the science focus for Curie is solar weather, solar radio bursts, coronal mass ejections, and tracking them and the radio signatures as they propagate out from the sun. So this is a mission out of SSL at Berkeley. And finally, I want to highlight Sunrise, which is a mission out of JPL and Michigan that is a larger constellation. This is 6U spacecraft, and now at a higher orbit. So Aerovista and Curie are in low Earth orbit. Sunrise will be in geostationary orbit, much higher. So if you're interested in Sunrise and the really cool technology and science, you should talk to our next speaker, Joe Lazio. He's the project scientist for Sunrise. So we're getting there. These are all interferometric missions. They will have some angular resolution, better than single spacecraft. So we're making progress, but there's still just a few elements. So the sensitivity is fine for really bright things like the Earth's aurora or solar radio bursts, but to get to these astronomy applications like exoplanets and cosmology, we need more sensitivity. So I want to briefly mention a concept that I'm working with a team to develop. We call it the Great Observatory for Long Wavelengths, or GOLO. And we're working on a concept study funded by the NASA NIAC program. And I know there's some NIAC folks in the room, so we appreciate the support. We're having a great time with this study. The concept is a free-flying interferometer that is a constellation telescope. A telescope made up of many parts that are reconfigurable and it can grow with time. So we want to put this far away. This is outside of the Earth orbit part of the title of my talk. But this is something we're working on. We'll have a report out towards the end of the year, beginning of next year, so stay tuned for this. And I want to note that I think the lunar far side arrays and free-flying constellations like GOLO, they're complementary. They have their own strengths and weaknesses, right? And for the constellation concept, we wanted to take all of the innovation from the mega constellations with none of the bad effects on astronomy, in fact, use them for good. So, we can build this up over time. We can take advantage of mass production. We can replace pieces when they fail. You just send up a new one, no problem. And finally, you can reconfigure a constellation like this. You can change the baseline lengths. You can change the baseline spacings. You can make a dense core, or you can have a much more evenly spread set of spacecraft for different science applications. So the lunar far-side arrays and something like GOLO, they solve the sensitivity problem. They have more antennas, they'll be more sensitive, and they will allow us to begin listening for the exoplanets in our local neighborhood and learning about their magnetic fields, maybe their moons, maybe the space weather in those systems that will have an impact on habitability. So I want to leave you, again, with this beautiful multispectral view of the Milky Way, our home galaxy. A lot of work in technology development, in data reduction, in engineering, in evolving science has gone into producing all of these images. Decades of work, thousands, probably tens of thousands of people have contributed to these images. So this is a huge achievement for us as a species. And there's just one little piece that we still need to fill in, and that's going to be the work of the next decades. So I'm really excited, hopefully in my lifetime, to see this slice filled in and maybe hear the songs of our local neighborhood exoplanets. Thank you.